Everybody. Welcome to this tutorial. Let me just take a minute to share the screen. All right. Can someone confirm that you are able to see the screen and you can hear the voice?
Yeah, we can see the screen. We can hear you clearly.
Okay. Thanks a lot, Jose. So maybe I will start off with an introduction and then the way the tutorial is organized. Let me also figure out the right way to. So, Jose, is there a suggested way to handle questions? Should I be looking at the chat window?
Okay, so we have a volunteer student. She will be monitoring this chat, and if something comes up, then she will let you know.
Okay, good. Okay, fine. So then I can focus on the presentation itself. Of course, feel free to interrupt with either typing something into the chat. Yeah, thanks, Jose. All right, so let us start off. I am Preeti Ranjan Panda, and I have with me Shailja Pandey, who is also on this presentation. And I'll start with introducing ourselves, and then we'll move on to the technical content, the format of this tutorial, and then we'll move on to the contents. So like I said, I'm Preeti Panda. I'm a professor in the Department of Computer Science and Engineering and School of Information Technology at IIT Delhi. What we have here is a presentation on thermal challenges on 3D memory. I have with me Shailja Pandey. Maybe Shailja, you can turn on your video for the introduction. She is a senior PhD student about to complete her thesis, who has also extensively worked on these issues that we will be talking about on 3D memory and the system management issues that come up in the context of handling thermal challenges. So yeah, we generally work in the areas of thermal challenges, power optimizations, and in general, system level implications of emerging memory technologies, emerging packaging technologies like 3D, and so on. So that's the introduction about us. Then a couple of words about the format of this tutorial. We have 2 hours, and overall we will have first the discussion in this lecture format. Of course, feel free to, it's not necessarily a one-way lecture, feel free to interrupt with questions, but we will have first the discussion using the slides, and in the second half, Shailja will take over and will continue the discussion in the form of a hands-on tutorial. Hopefully the instructions on the setup had you have already received, and you have already done your setup. If not, there is still enough time to complete that setup between now and the time that the tutorial will actually start. If you have a Linux system, 1 hour should be enough to complete the setup. But whatever the system is, hopefully you have you got that message in time and were able to do the setup in, and that will be in time for the second 1 hour that we have over here. So that's the format. We'll spend the first hour discussing some of the challenges, interesting new system design problems that come up in handling 3D stacking. Now, our focus is primarily on the 3D memory, but the problem of 3D stacking is a more general one. Was there a question? Okay. It's a more general one. You can stack cores, you can stack SRAM, you can stack DRAM. So a number of different technologies could be stacked using 3D packaging ideas. And so that's the overall topic. While stacking can be anything, our initial discussion will be about specific things we can do in the memory space. In the 3D memory space. That too is a technology that is rapidly evolving. So that's what the focus is. But the tool itself that we will present and we will do some simple experiments with, that's capable of different types of stacking. You can have CPU stacked with cores, and as long as the elementary requirements are met with respect to generating a power trace that could be then used for studying temperature effects and so on, that should be fine. In some ways, some of this exploratory study, system level study that we are doing at the high level is independent of the specific function of the systems that are being studied, whether it is a processor or a memory or any related technology. It's also independent often of the specific technological details like geometry and so on, as long as the power trace that we need is there in an accurate form, and as long as our characterization of the material that makes up the system, the 3D stacked system, as long as both of these are authentic, the simulation is authentic, and therefore interventions of various ways, including movement of data, including allocation of tasks, and so on. These are general system design problems, and all of these could be studied with the tools. So that's just an outline of what the format of the tutorial is. We can go into some detail now. Just motivate the problem and dive in with respect to the technical content. All right, so our outline is as follows. We'll talk about the 3D stacking and the thermal challenges that are involved. We will talk about some application specific. So we'll talk about some of the solutions for these challenges that we are seeing. We will also talk about some application specific intervention, meaning that if I had some ideas, if I was already aware of the nature of the application, the details of some internal structure, if we have the background of, then we could use that to further refine the system design ideas that come up here. So we will take up a particular example of neural networks, and we will see how we can subdivide that into our tasks in that specific context, and then pose the system design problems. So that's the main content. We will also talk about the simulation infrastructure, Comet. That is a tool that we were involved in and significantly have contributed to, but also it is an inter-institutional effort. There are other contributors from universities. We'll talk more about it. And to continue that into the second half, there is a hands-on tutorial that will be presented by Shailja Pandey, and she will use a different set of material and guides for us to go through the tutorial. Okay, so let's talk about 3D stacking, but taking the DRAM as an example because that is a popular instance of a commercial system in which stacking was first implemented, and because the commercial systems started with DRAM, it's more than 10 years now that this went into the market. Several generations of the 3D stacking in DRAMs that has gone through. It continues to evolve. It's a challenging area. It's a very popular area with respect to bandwidth that it provides. This through silicon via, that's the TSV. These are essentially what are connecting the multiple layers. Right, so the interconnection is provided by those layers, and at least in the early incarnations, we had this format called HMC, Hybrid Memory Cube, where we had one channel, memory channel consisting of sections of the die that are vertically aligned. That was one channel. So the picture here is a DRAM system, a 3D DRAM system with 16 channels. So 16 coming from the 4x4 grid here, and each of the channels was a vertically aligned set of 8 die. Okay, now why is it interesting? Of course, so there are a few important advantages. One is that it is compact as opposed to 8 different memory chips that are scattered around on a PCB. So area and volume wise, there are some nice advantages. Bandwidth wise, there are some important advantages. So if you have 16 channels here, then essentially there are 16 independent access streams that we have to the memory, and therefore the channels, therefore the ability to support multiple channels in one 3D stack structure is very attractive, not just from a volume point of view, but also from a performance point of view, because it affords much higher bandwidth. Now, how many channels are there? That depends on these on the specific configuration, and the standard itself has been evolving. But initially, the HMC essentially had vertical mapping, but later on, the several generations of HBM that's there in the market, essentially the mapping. So what we are talking about mapping here is the way the logical channel numbers map to physical locations of these blocks that we have on the dies. So there are 8 dies, but we have bank structures within it, which is not shown here in the picture. But the way the banks are laid out corresponding to a logical channel, that's what is a mapping function. All right, so that's there are advantages with respect to space. There are advantages with respect to performance in the form of higher bandwidth, but there are also advantages with respect to latency, just because the TSV structure, because it is so compact, it leads to a faster access. It's so faster to take data from the internals of the DRAM structure onto way to processor or whoever is requesting the memory data for us. So it's important to note that this stacking can be done with memories implemented in various technologies. So essentially, what goes inside that bank structure of the memory need not change at all, but the evolution here, innovation here is at a higher level. The interconnect is what is different here, and because the interconnect is shorter than earlier, where you had to route wires across the PCB to the different dies, it is faster. So the latency is lower for this structure, but this is independent of whether there is any further innovation that goes on in the internals of the DRAM, like the bit cells and so on. So it is a lower latency primarily because of the interconnect, at least to start with, although you can have other innovations. This is a hot area, and there are lots of innovations happening, including in research, which of course is mindful of the fact that it is an overhead. Accessing data from the memory is an overhead. For the further computation that's going to happen, and therefore one of the alternatives, of course, is that you can try and push some compute structures into the DRAM, or the other way around, to address this phenomenon of the memory wall, where too much time and energy is spent just transferring of data. That is a topic that we will not be talking too much about, the compute in memory, but that is an independent and orthogonal optimization that one can certainly perform in this stacked architecture, where each of the blocks that we have here that are stacked, we can further innovate with respect to the way memory is structured there, whether at the bit cell level or sense amplifier level, we have further innovations, or also more of the more radical type, where we also put in some compute structures into the memory bank and integrate them in some way. We will not talk more about that, the compute in memory part. For now, we'll be talking about, just the 3D memory part. All right, but of course, there are some costs that are involved here. For now, as long as the volumes are lower, there is a higher cost for this structure. So you can think of various ways in which this can be useful. It could be like the equivalent of a cache in the system, which is closer to the compute, but is also higher cost, and therefore you don't have larger amounts. So as a background to this 3D memory structure, you could also have your standard planar 2D structures for the DRAM, where the capacity can be much higher. So there are some different use cases for this technology. Okay, now what is the industrial status? It's a good idea to just review this before we go ahead into its control and its system level implications and the research that goes around these packaging ideas. First of all, even before the 3D, which is that structure here in the middle, where you have CPU that is also integrated with DRAM. So there may be CPU, SRAM, DRAM. So the one at the bottom here, we have CPU, and maybe caches are there at one level. Maybe DRAM is integrated with the other. Ideally, all of these are stacked independently of each other. We might move into such a future, but commercial interpretations are there, which are more limited, but this is an active area, and a lot of work has already happened in terms of achieving at the level of commercial scale some of the stacking that we are talking about. What we have on top is what is called a 2.5D architecture, where essentially there is an interposer structure here on top of the PCB that makes it a faster interconnect between the different stacked structures. So you could have CPU that is stacked next to a 3D memory. So this is also, so it's not that the CPU is stacked with the DRAM as earlier, but it could be actually different chips that are as far as the packaging is concerned, sharing this interposer, and there are multiple chips. Okay, there is some standardization effort, like I had pointed out. Started off with the HMC, but we have had several generations of the high bandwidth memory that is a newer. No, those are the generations that have that we have gone through, HBM3, and further evolution. That's what is going through. That's what the standardization bodies have gone through. And there are several manufacturers that have attempted designs in this space. Samsung, SK Hynix, Micron, and so on. In terms of larger systems where these where this kind of technology has been used. It's used in various parts. GPUs have been put out by NVIDIA, where Essentially, they are interfacing with 3D DRAM structures, SBM structures. AMD has put out designs where you have processors stacked with cache. There are also Intel products that are AI, targeting AI domain, accelerators targeting AI domain, where such 3D memories has been used. There is at least one line of processors and one line of stacking technologies that Intel um, uh, had commercialized, where essentially the idea was that you can stack anything with including CPU and memory and so on. It's an active area. We can expect future generations to achieve more and more integration with respect to the 3D stacking. Okay, so with that introduction, let us get to the main topic of the tutorial, which is about thermal issues that come up in the context of vertical stacking. So here is a simple experiment. Suppose you have a uniform load activity across all the memory banks. So these are memory. This is a 3D memory. Essentially, you have 8 layers of that memory, and what you have here, what's shown in each of the layers is a bank, and let's assume that the what's the question? Okay, we continue. So the load may be uniform, but still, one thing is that there is a leakage power that the system undergoes at higher temperature. This is independent of any activity that takes place. And what happens as a result of the leakage power is that there is some buildup of the power. What you have on top is a heat sink, and what you have at the bottom is essentially a PCB, which is like an insulator, and there is not much dissipation of heat that is there from the bottom. Most of the dissipation is happening from the top, and also not much from the sides, although this is a little bit of an exaggerated dimensions just for illustration, but actually the vertical distance is not very much. So what happens is that heat accumulates in the bottom layers because it is far away from the heat sink, and the dissipation of heat is good from the top layers, because of which you may have this gradient that you see in temperature. The bottom layers are hotter and the top layers are cooler. This is a phenomenon that has been observed by researchers and by the industry, and various solutions, of course, have been proposed. We will look at what we can do about some of this, but this is essentially a physical effect that is known, and the problem at the system level would be essentially what can we do about it, and if I can export this knowledge of the physical effects to the system designer, what are the knobs that are available to us, what are the opportunities that are available to us that exploit, essentially, that address this performance versus thermal trade-off. Okay, you would like high performance, which means that you would like to keep everything on running at the highest voltage all the time, but there is this safety limit issue that if the temperature goes above a certain threshold, then the system becomes unreliable and you have to do a lot of other things. So we can pose this system design problem in various ways, but essentially the system, the simplest solution is that the system needs to stall if the temperature exceeds a certain threshold. The stall means that the performance is affected, and if the performance is affected, then of course it is back to us as system designers to come up with interesting solutions so that the effect on performance is minimized while always respecting the thermal thresholds that are imposed on the system. So it could be that I pose the following system design problem where I say that 80 degrees or 85 degrees or 105. So I take one of those limits and say that the system, any part of the system must not exceed those limits. And within that, though, I have full flexibility to do anything I want in a system. From a system design perspective, I can move my data, I can move my tasks, I can move I can change voltages, frequency, and so on. The standard tools that are available to us, all of that we can do, but we are supposed to respect the temperature limits. So those would be the high-level exploration space for us. And let's move ahead with an illustration of what might happen. What's being shown here is essentially you have the condition is that the activity is uniform, access activity is uniform, and because of the reasons that we talked about, the heat sink is there on top, there is nothing at the bottom. So you see this kind of a temperature gradient that is building up in the sense that the layers that are furthest away from the heat sink, they are becoming hot. Even there might be some secondary phenomenon that says that the central channels are hotter because they have more neighbors than the channels at the side. So what we have here is like the top view of the bottom channel. So the hotter channel is what's being shown. What can I do? Now, this is where the system level solutions come in. Maybe we can move some of the data. You take the hottest channels and back up some of that data into offline 2D memory. Of course, if you do that, then there is an impact on the memory system performance because buses are occupied for that time. So there is an overhead in transferring the data, but it might still be okay. It's still better than stalling the system completely, which would lead to an even further overhead on the performance. So it could be that maybe there is backup that is happening to the 2D memory. Maybe after the backup, I can turn the channels off so that they cool down, and it also helps the surrounding channels that way. Because of its cooling down, the adjacent channels might also be cooling down, while the corners still remain hot. So maybe this could be one of the implications. And we could do the same thing, which is whichever, if it is still too hot, then we take at a secondary level, maybe data located in the corner channels and move. So some such activity I can go through, and that can be my overall system design space. Initially, a simple one in which no further changes, but I essentially do a data migration kind of an activity. And that could actually be my first level of defense as far as the addressing of the thermal challenge is concerned. So, of course, I need not stop there. We should recognize that the problem is more complex than what is shown here. We started off with what is just the memory structure, but in general, memory is only one part of the system, and the general system has a processor, memory, accelerators, and other things. So let's try to expand the the exploration space into also having a CPU, but it is still a structure in which there is a multi-core CPU, but that is not integrated into the stacked memory. So the memory is stacked separately, and there is a multi-core processor that is separate. Maybe they are physically located nearby in the form of a 2.5D architecture. So let's to illustrate some system management issues that come up in a space like this. Here is an example. Suppose it's a 4-core system, and this is a 4-channel system for me. And what I have shown here is essentially the bottom layer. The colors here indicate that on the CPU side, what we have at the 0 and 3 in red color, those are the compute intensive workloads. So those are the ones that keep the CPU running all the time. So they keep the CPU busy. And so there is some so the CPU gets hot because of so there's a temperature effect now on the CPU because of the compute intensive nature of the workload. The other two CPUs have a memory intensive workload. So this is and for illustrative purposes, let's assume that each of these processors has its data mapped to one of the channels. This is not the only way to organize our data in channels, but here is one way to achieve isolation of the different processors' data from each other. So the CPU 0 essentially is using the channel 0 of the memory for storing its data. Accesses made by the CPU 0 are affecting the channels channel 0, and by 3 affecting channel 3, and so on. So essentially the implication may be something like this, where you have CPU 0 because it is a compute intensive application that's running, is not heavily utilizing the memory because there are not too many accesses to the memory. On the other hand, the memory intensive applications that are running on the CPU 1 are so those are affecting the memory accesses to channel 1. So that's why the channel temperature may have a different profile, where 1 and 2 actually the memory channels are getting hot because those are memory intensive workloads. So you can see that they are somewhat orthogonal and opposite of each other. 0 and 3 are getting hot because of CPU 0 and 3 are getting hot because of the compute intensive. That's keeping the CPU busy. And 1 and 2 channels are getting hotter because the corresponding CPUs to which these channels are mapped are essentially running memory intensive. So the CPUs are cold, but the memories are hotter. Of course, this is just an illustration, but there's an important point to be made. What happens? What do you do when you have systems getting hot? Of course, there are some thermal sensors that are there. Nowadays, they are there in the CPU. They are also there in these memory structures. They're also there in stacked memory structures. So we can actually find out what is happening with respect to temperature in each of the memory layers and memory banks and so on. So there is instrumentation of that nature that is already either there in commercial systems today, or they are prescribed by the memory standards as they evolve, just to aid us in the system management decisions that we are taking. All right, so we detected that. And what do we do about it? There is a dynamic thermal management that is well known, and you would usually resort to such thermal management or DTM mechanisms when you have the temperatures approaching some limit, right? Temperature limit. So what can you do? Maybe you slow down. Maybe there is a voltage and frequency scaling that you do. So one of those standard system management tools you would probably adopt, so that maybe these two processors that were getting hot are slowed down, right? So that's one of the activities. So that reduces the temperature. Of course, when you slow down these two processors, there's also a secondary cooling that happens for the memory channels that they are connected to. So these also become so whatever the temperature was, that further reduces of the memory channels, just because the CPUs themselves have slowed down. Okay. Correspondingly, you could also do the thermal management on the memory side, where you have the memory channels 1 and 2 are getting hot. So you could try and turn off some of the heater channels. That is the mechanism that we've seen so far. If you turn them off, then of course the corresponding processors that are running those programs, they also would have to get stalled, and therefore that reduces the temperatures here on the memory side. That would also reduce the temperatures on the processor's side. So secondarily, it also cools down the cores, and you can see that there is as a result, there may be some kind of an overcompensation. You are cooling things on both sides, both the processor side and the memory side, and therefore you really need something like a more integrated strategy that is aware, that's not independent, like earlier it used to be, just for the processor or just for the memory. But what this illustration is pointing out is that you need really an integrated strategy. There's an algorithm that's doing thermal management that needs to be aware of what is happening in both the sides, sensors from the CPU side, sensors from the 3D memory side. Both of them need to be observed so that the problem is a joint problem on the processing side and on the memory side, and the algorithm also needs to jointly address that. I'm not going into the mechanisms involved, so what the details of such an algorithm would be, but it's important to motivate that this is a new space that evolves in the system design world, where now joint problems of these nature come up. The thermal problem comes up as a new effect. The gradient that is there in the temperature, that comes up as a new effect that we need to address. The need to jointly address the CPU and memory together, that comes up as a new effect. So there are a lot of new challenges that come up. The overall, I would say the problem is still new. A lot of research is going on. Of course, commercial activity is also there in this space, because we do need to make sure that our systems are operating safely as far as the operation is concerned, both with respect to, so of course I need high performance, but I can't give up on the safety. The thermal imposes a safety limit for us to be aware of. So let's move on to some other related phenomena that happens here, and newer problems that come up in a space like this. So this is a multi-core processor that is similarly stacked maybe next to a DRAM, not above or on or below the memory, but this is adjacent to the memory. So here's what might happen. This is what we are showing here is an HBM structure as opposed to that HMC structure that we had earlier. In this HBM structure, the channels are organized like this. You have channels, 8 channels in this system, but they are horizontally laid out. 0 is next to 1, 2 is next to 3, and there are these 2 stacks, stack 1 and stack 0, that are essentially lying on top of each other. So you have a stack of 4, and there's another stack of 4. There's the stack 1 and 0. So one of these processors might be mapped to one channel, and that channel might be just what we have here, spread across physically across multiple locations in this stack structure. This is what a modern HBM system, memory system, is likely to be. Okay, so if I have a processor here that's accessing data in channel 6, the channel, and you have some other processor that's also accessing our channels, and what might happen is that there is some heating that is happening. I have done my mapping, and because of the activity in the channel, we have aggressive memory requests that are being issued, and therefore there is some stalling that I might do of the CPUs. In the general case, I need to do something about that, and that's what leads to maybe some further application specific intervention. So you see that the nature of the heating problem is similar, although this is a little more complex structure. Now I have physically, there are 2 locations. It's not just the furthest location or one layer that is getting hot, but the heating is actually spread out across various parts. Nevertheless, I need to be aware of, as the system designer, what is the consequence. So because of the mapping, there is some consequence on temperature, and therefore I need to address this system of what to do, considering that first I can anticipate what's happening because the mapping structure is known, channel mapping structure is known, nature of the applications might also be known, and if I have some idea about the applications, then what kind of application-specific intervention can I do? That is the next question, and we can give some thought towards solving problems of this nature. One is, I know nothing about the application at all, and I just observe temperatures, I observe other things that are there, like activity, memory activity, and based on that I make a controlling decision on the system. But we need not stop there. We can go further into specific applications. If I had known, then can I do something about it, considering that I know how the system is going, memory system is going to behave. So so our overall design philosophy can be sort of a long term, which is what the processing in memory and other ideas are exploring. But the short one can be that we are closer to traditional platforms and we customize our solutions for that specific domain. And since neural networks are a popular domain, we could actually illustrate this application-specific intervention with an example of a neural network. Here, these layered structure of the functionality of the neural network could be used to serve as tasks for us, since they execute in phases in some natural way. The memory access behavior can be characterized. We have some idea about what is happening in convolution layers, fully connected layers, and so on. I can characterize them earlier, and the kind of memory footprint that is generated, all of these, because these are regular computational structures, we can have a good idea of that footprint, although quite a bit of it might also be generic. But I mean, it might be some of it, much of it might be generic, some of it might be specific, but we can certainly do some pre-characterization so that we have an idea of what is coming up. So this is an example of such a characterization. If you take some neural network like AlexNet, and if I just look at the number of DRAM accesses and the way it evolves with time, you can see that the system is stable the graph is stable for extended periods of time, telling us that these are basically the layer boundaries, what you have here, right? The transitions are the layer boundaries. So in different layers, the behavior is different, but within a layer it tends to be similar, and therefore this observation can be easily used to inform an algorithm or a dynamic thermal management strategy that takes some decision during a layer and maybe changes that decision for the next layer, and so on. So you can see that pretty much depending on which data structure that you're observing, the transitions are similar, right? At different times, you have similar transitions, and that depends on what which is that you're. So depending on what policy that you are using, you may have one or the other, but the behavior is not very different, which is that there are long periods for which you have similar behavior, and therefore I can take system management strategy once in a while. I don't have to take very frequent decisions, and I can expect that similar behavior would be observed for longer periods of time. So I can take that into account in a management mechanism that I formulate for applications of this class. What we are seeing here is for that VGG16 what the temperature profile looks like as you go from left to right in time. You see that there are changes, drastic changes in the temperature profile. Those essentially correspond to layer transitions, and each of these layers is a phase. So what we can do is, what this graph is telling us is that maybe we ought to be looking out for these transitions and take appropriate action when the transition happens, because between the transitions there is quite a bit of time for which hopefully we have taken the right decision, and we can stay at that decision for some period of time. So within that, we can ask several different questions. I will not go into all the details, but I could think of a task mapping problem that comes up, what is the task? Say I have this task sequence that is presented to the course, and I know what kind of task it is. And since I have profiled those tasks earlier, based on what is happening on the processor side, what's happening on the memory side, I can maybe take some intelligent decisions here with so that my overall execution of task, the time is minimized. My temperature is always below the critical temperature, that I will try. Maybe once in a while there are thermal stalls, but I'll try to reduce the number of stalls, the number of amount of time that I spend in the cooling the system down, because that is the time that we are not using, that we are not utilizing the resources that we have. So that is some overall strategy. I will not go into too much detail of these, but you can think of a core to channel mapping problem. You can think of a task to core mapping problem. I have to divide that neural network into tasks and take decisions of what task would be executed on which core. There is a task migration that I might do. There is a swapping of applications that I might do. So the dynamic thermal profile would be observed, and based on that, I would take different actions, maybe migration, maybe swapping, maybe a voltage and frequency scaling that is aware of the tasks that is happening, and therefore is aware of the profile that I'm going to need. And finally, there is also the low power state control that may be available for me in the DRAM, so that I could also do. So these are like different system design problems that come up for me, and just visually pointing out some of the activities. I could actually classify my cores into heavy ones, medium ones, and light ones. And the ones that are the channels that are closer to the heatsink, maybe I put relatively heavier, heavy with respect to memory access. Maybe those tasks can go there, and others can go to the medium. So the medium can take some other channel, lighter ones can take some other channel. So that is a mapping problem that is available to us. There is also a task to core mapping. So anyway, and depending on the kind of tasks that I have, maybe I can distribute them accordingly, because if the heavy, the ones I had earlier, which was these heavy group, right? So that's the ones that are closest here to the heat sink. So correspondingly, maybe I can make my decisions if there is a light, there is a layer so just like the cores can be classified into heavy, medium, and light, maybe layers can also be classified into heavy, medium, and light. And I can say that the light task can go anywhere. The medium tasks can go into heavy or medium, and I can say that okay, that heavy tasks can go only into the heavy cores. So this is just so that we want, if they're going to heat up the memory channels, then they should be closer to the heatsink. So some such task to core mapping decision can be taken. Some of these details I'm omitting, but essentially I'm just illustrating the system design problems that come up in a space like this. There are migration problems that might come up. Maybe initially their cores are empty, and after some time, at time t1, there is a certain profile of temperatures in terms of the tasks that have been allocated to them, and maybe there is an opportunity for migrating the tasks here, perhaps. So what happened here is maybe I decided to move some task from one of these upon a layer transition. The profile of that expected temperature profile might change. So I might move that task from one of the cores to a different core. So that's my task migration. Similarly, maybe I can swap some applications upon layer transitions. So I can maybe think that so I have 2 and 9. So these two maybe I can swap just because enough space might not be there in one of the tasks. And so in some order, I can do application swapping, I can do migration of tasks, and I can also do voltage and frequency scaling. These are the tools that are available for us if we don't have the opportunity to do swapping or migrating. Maybe I can just slow down some of the cores so that's what happened to us here. So one of these cores, this core 13, because of the change in the application, the change in the phase of the application, where we went from one phase to the other phase, that was more that would require us to move it to the heavy region, but heavy region there was no space, so I essentially slowed down slowed down the task so that the requests are also slowed down to the memory. So these sort of tools are there available to us, and in general we can go through a finite state machine, a power state machine that is observing the 3D memory system. Over a period of time, maybe there is some heating that is being observed, and that heating channels may be heated channels, maybe they can go into, I can move them into standby mode, and once you have recovered, maybe you are back to active, and you are in general in this loop where you are fully active, and when some heating happens of the channel, you move some of the channels to standby mode, and when they are back, when they have recovered, then you move everything back into active. So that kind of a state machine might be used for us. Just to indicate some of the important system level tools and knobs that are available for us. So that is the just a view of the system level.
Professor, can you hear me? May I ask a question?
Yeah, please go ahead.
Yeah. When you mentioned the characterizing the behavior of different layers of the DNN model,
Right.
is there any standard criteria to do the classification, or based on some profiling? Because different deep neural network might have different behavior, and how do you generalize the criteria of the standardization?
Yeah. Thank you for asking this question. It is an important one. It is true that when faced with a completely new network, then some profiling is needed. At least as a one-time profiling is needed of a new neural network that we might want to implement on a system like this. That profiling can be offline, but for us, so there are two approaches. One is it can actually be completely dynamic. What the application-specific intervention I'm talking about here is one where certainly every neural, if it's a new neural network, layer-wise characterization of what to expect there, what kind of activity to expect there, that we in an offline mode we do some profiling. That profiling can be of various kinds, but primarily what affects here is the rate of the memory accesses that you expect the system. So this is a profiling. It's jointly done with so with the computer infrastructure, the CPU side that is going to put out those requests, of course, or accelerator, whichever is actually connected to the memory system. But essentially, what we observed is that the graph that I showed earlier is one that seems to hold across a large category of neural networks. Within the layer, the profile is similar, and across layers it might actually be changing. So a couple of things. One is the profiling of those layers. Second is the transition of the layer that is controlled in like a higher level entity in software or something like that, and that the fact that the transition has happened, maybe for now can be we need to be informed so that we can respond appropriately with respect to what is you expect in the layers. But the fact that the layer is what to expect in the layers, that is somehow known in advance, that is what we are assuming right now. Maybe even that assumption can go in the future, but yeah, the argument is that a lot can be done if we are informed what is the layer, what is the network, what is the layer that is currently under execution. If even this much information is there, then there is a lot of interesting trade-offs that can happen in the system design space.
Okay, thank you very much. I have a small follow-up question. When the system like commit, when there's a couple of different neural network, so we should providing this kind of neural network together for this multiple DNN models, or is any
what we are relying on, of course I will go into more detail. I will introduce it later in the tool part of it, the hands-on part of it. My co-presenter will talk more about it, but essentially the things that that affect temperature at the memory side are two things. So there is a dynamic power and there is the leakage power. Now the leakage power is now there is now temperature is determined by leakage power. Leakage power is also determined by temperature. There is a circular loop there. That part of it can be, of course, modeled by the system. We have tried to model that in this infrastructure. If you leave that out, the thing that affects is the dynamic power. That's the one that is variable, and really it is one number. It almost translates to just one number, which is what is the rate. It's how many memory accesses per millisecond or per whatever our intervals are. Accesses per unit time. That is the profile information that we would need. With that, there is enough information for us to go ahead and build pretty intelligent infrastructures that are following the performance versus temperature trade-off.
Okay, thank you very much.
Yeah. Sure, thanks. So let me conclude this part of the presentation by just pointing out the tool that we'll study in more detail. Essentially, this is an open source infrastructure, an integration of several different simulations. There is a performance simulation that's going on, that is the Sniper tool. I'm not talking more about the tool themselves because these are actually pretty commonly used in the community. There's a thermal simulation done with Hotspot. There is a power trace that we need to rely on. So that for the compute part, MacPat, and there's a variation of these basic tools, MacPat and Cacti. So one is for the processor part of it, Cacti is for the memory part of it. Of course, different kinds of memories can be modeled with the Cacti, but essentially we can build through some layout generator and a structure like this. So that becomes an input to the tool, and what this is a snapshot of the system that shows there is a core layer, there are 8 memory layers, and what I've shown here is that the color is somehow representing the current temperature. So there is an application that is running. So if this is a 16-channel system, then there are 16 applications that are running on the performance simulator, and the per access energy is used from the models of MacPat and Cacti, and there is also a thermal simulation that is running simultaneously. All of that is happening together, and the features we will go into later. I just wanted to point out that what are the things that you can do. You can analyze the temperature profile. We can experiment with different policies, thermal management policies, task scheduling. That depends on the specific system design problem that we are taking up, the DVFS or memory power states, and the current status is that as of now, we are working on different aspects of the system. There is some limited validation against ANSYS tools, but essentially we have tried to keep it limited to current open source tools that we assume have also undergone some level of validation, like Cacti or MacPac. The informal feedback from the industry is positive so far, but of course the absolute numbers of temperature and so on that are there, that depends on the data. So it is, to some extent, it is limited to the accuracy is limited to the accuracy of the models and the data that we give, for example, power data, access energy data, and so on. I also wanted to highlight that this is a multi-institutional effort. Many people are involved. IIT Delhi was primarily involved here, but there's also a significant contribution from University of Amsterdam, Karlsruhe Institute of Technology. Supported architectures, we'll go into more details of this, but it could be off-chip completely, it could be stacked, so off-chip next to a core. It could be a core is completely integrated with the memories. It could be that they are connected through an interposer and so on, different. But there's just a snapshot of what the tooling looks like. There is some configuration and access generator. So that's my performance simulation that is going on, the CPU simulation with the Sniper tool. But there is an instrumentation of that is happening, and counters from here are leading into the models for processor and the memory models, so that I can convert my access trace into a power trace, essentially, and then I could feed that into the thermal simulator that is a hotspot based. What is shown in blue are the things that are new. The rest of it is still just the default tools that were available to us. So the output of these can be our memory temperatures and core temperatures. That's what is the heart of the simulation. But after that, I can have my DTM engine, in which I can have some default policies. But if I have new ideas with respect to system level management and DTM and so on, I can use that. And so that's the overall structure. And there is some visualization tool and output tools where we can observe what's happening as the simulation progresses. So just a summary and the future directions here. We have new technologies or emerging technologies such as 3D stacking and non-volatile memory and so on, all of that. When it happens, the natural question that occurs is, what is the impact all along the computing stack? And there may also be an opportunity to take some application specific decisions in SoCs that we are building. And what I tried to highlight in this presentation was what are those new opportunities when you have 3D stacking. Because of thermal reasons, newer opportunities arise. There is generally a lack of industry data on new problems like these. So while the inspiration was indeed from hints that were given by the industry, the data itself had to be still generated from various models. Some of that, of course, can improve over time. We can have better quality data, but what we talked about is some basic infrastructure for studying this, and just some a deeper look into what kind of new system design problems that come up in this space like this. So a tool like Comet that we'll study in the next part of the tutorial gives us the ability to do an early evaluation. So let me conclude this part of the presentation. The work is part of the MARG group memory and embedded architecture research. We work on problems related to memory management, emerging technologies with respect to 3D, non-volatile, and so on. There is a hardware accelerator. So some of this that I talked about is part of both the management of the memory side and also application specific intervention side. This work has been sponsored by companies like Intel. So much of the inspiration came from companies like IBM and Intel and NXP, SRC. So these are the the people who have provided important inputs to research that I covered. And I should say that much of what I said is based on the PhD work of two of graduating students, Lokesh Sidhu and Shelja Pandey. And what I covered here is a summary of ideas that are explored in more detail in these publications that I have pointed out here. So let me conclude this part of the presentation and hand over to Shelja, let me stop the sharing. Yeah, Shelja, you can take.
Okay, thanks. Yeah, is my screen visible?
Yes.
Okay, great. Yeah. Hi, everyone. So now for this part, now I'll be taking on from here. So as we have seen so far about the thermal problems in 3D memory and of course CPU as well. So what we are going to do in this part of the session is that we are going to run some basic simulations just to see that how our tool Comet it works and how can it be used by different in different researches. So basically the first thing that I would like to highlight here, although we had seen good motivation so far from our presentation, but still just to summarize, why do we need thermal simulation is, just a second, I'll minimize this part. Yeah. So basically the power density and the cooling cost, they are rising exponentially and because of the 3D stack architectures. And the situation is that, and actually the situation was similar even before, that power and temperature aware design, it's a first order concern. And for such problems that we are facing today, where we do not have access to commercial products and we do not have access to actually control and monitor and then tweak temperature management policies in commercial products, we rely on thermal simulation infrastructure. Yeah, so we rely on thermal simulation infrastructure so that we can perform a design space exploration for modern architectures, and we can develop efficient runtime management techniques for thermal and power behavior. And of course, the thermal aware architectural studies can be performed where there is a specified, a predetermined thermal constraint and power budget on the architecture that we are studying. So keeping in mind this requirement, our group has developed this tool called Comet, which is an integrated performance thermal simulator. And it is an interval-based tool that I'll discuss next what it exactly means. And this tool paper, it is published in ACM TACO 2022. So this slide here, it shows the overall flow of our tool Comet, where basically what happens is that it's an integrated performance and thermal simulation. So the performance simulators such as Sniper or GEM5 or any other simulator, it will run and provide us some performance counters such as memory access counts in our case. Those access counts, they will be fed to a power model. It could be CAPTI, it could be MACPAT, depending on what power values we need. And these access counts are then converted into core and memory power, which are fed to a thermal simulator along with the floor plan of our architecture, where floor plan will specify basically how many layers are there in our stacked architecture, how many cores are there, and what is the configuration of a 3D DRAM that we are considering. I don't know why is this exiting again and again. Yeah, so after we feed in the power and floor plan to a thermal simulator, the thermal simulator will give us core and memory temperature, which could be fed back to a DTM policy that is implemented on the performance simulation side. and the DTM policy, which will monitor the memory and core temperatures and take appropriate decisions. That has been indicated in the past session, which might include like data or task mapping policies, or doing some voltage frequency scaling, or setting up appropriate power states of core and memory. So the DTM decisions, they are implemented on the performance simulator side. And as the output of this whole block, we can our tool Comet, it reports the performance and power and temperature stats for every interval. So basically that's why it is called as interval based simulation, that at every interval certain actions will be taken based on what temperature or cores are being what temperatures is being attained on the CPU and the memory. So as we already mentioned that Comet supports various architectures such as an off-chip 2D memory architecture, where a core and memory, they are organized in an like the main memory is off-chip to the core. The next one that Comet supports is off-chip 3D memory architecture, where we have a core and then we have an off-chip 3D memory comprising several DRAM layers. Next, we have 2.5D architecture, where core and memory, although they are separated, but they are part of the same interposer. And lastly, we have pure 3D stacked core and memory, where the core could be stacked either on the top of the main memory, or it could go on the bottom. So these are the currently Comet supports performance and thermal simulation of these 4 architectures. Going forward, this is a slide which will detail exactly the workflow of the Comet tool. So what we essentially do is that we have a configuration file which actually represents our architecture, our underlying hardware architecture. And we have several performance parameters that are specified in the configuration file. They are fed to a performance simulator such as Sniper. And we have extended the vanilla Sniper simulator with an access trace generator, which will report memory access counters and other performance counters at every interval. The performance counter related to CPU, they will be fed into MacPack power model, and the access counters of memory, they will be fed to a cacti power model. And using these power models, we receive the core power and the memory power per interval. Next, these two things, along with the memory floor plan, they will be fed to the hotspot tool, which has been extended in Comet to support a leakage power model, and it will output the memory and the core temperatures, which are fed to a DTM engine that will take the appropriate decision and either throttle the core or throttle the memory, or whatever the policy is implemented, appropriate actions would be taken. Yeah, as I mentioned earlier, there are a series of other output statistics that will be, the files will be created and displayed. So moving forward, after understanding this workflow of Comet tool, this slide here, it represents a snapshot from our output of the Comet, which represents a thermal map of core and memory. So here you can see that we have a core and we have an off-chip 3D DRAM, which comprises several DRAM layers. So initially, when all cores are idle, which means that both core and memory, they are in the cool state because no application is running. So no dynamic power dissipation is happening either on the core or on the memory side. Now, when some cores become active and they are running certain applications, the color starts to change, which means that memory and core, both the temperatures start rising, which means that there could be heating depending on whatever is the thermal limit that is specified for this entire system. Now that's where we need to kick in some dynamic thermal management, and towards that. So basically, why is this heating happening is because first of all, the power density is very high in the stacked architecture. And there are two components of power. One is the static or the leakage power, which is which exists merely from the on state of the device, the transistors. And the other is the dynamic power, which arises from the aggressive memory activities that are initiated from the core. So this kind of power dissipation, it leads to higher temperature. And of course, there is a positive feedback loop between leakage power and temperature. So then the power consumption tends to rise. Now, for systems that are working under thermal constraint, we require dynamic thermal management. So in this part, I'll discuss some preliminary thermal management strategies. So basically, what is the role of dynamic thermal management policies here is that these policies, they will periodically monitor the temperature, and once they see that temperature tends to exceed the thermal limit, they will reduce the activity of the hot functional units. It could be core, it could be memory. So in today's lab, we'll learn about low power states-based DTM policy for DRAM. What is meant by a low power state-based DTM policy is that the rank of a 3D DRAM, it can be in one of many possible power states. For example, it could be in an active state or standby state or power down state. So in the active state, what happens is that the channels, they are able to service the memory accesses. In the standby state, it is a low power mode where the channels, although they are in the on state, the transistors remain on. However, the memory accesses get stalled at the memory controller. Memory accesses cannot be serviced. And then there is a complete turn off state, which is power down state. So in our in today's discussion, we'll show a DTM policy. We'll actually implement a DTM policy which will regulate the power state of memory ranks so as to control the temperature from exceeding the thermal limit. So this is the state diagram that we have seen earlier, where the memory is in the initial state, and once one or more channels are heated, which are shown by red colors here. Yeah, sorry about this interruption. Yeah, so initially the memory is in the initial state. However, once one or more channels are heated, the memory, those heated channels, they are put to the standby mode, where the memory accesses are temporarily stalled at the memory controller. And when the heated channels recover, the memory goes back to the active state. So this is the state diagram. In a way, it represents a dynamic thermal management policy. So in today's session, basically now we'll start the hands-on session. So I hope everyone got access to the manual that we had shared maybe I think couple of hours ago. So for the attendees who have Ubuntu based machine, it shouldn't be a problem. We can even if you will not able to install and complete the prerequisites, we can do it online, and it wouldn't take much time. However, for attendees who have access to Windows machine, it might be tricky if they do not have virtual machines installed for Ubuntu on their Windows machine. So yeah, maybe I'll get started on my machine, and people who cannot do it in parallel, they could just follow my the simulations in my machine. And when they try it on their own, if there are any questions, please feel free to reach out to us. Yeah. You can also run the instructions side by side on your machine, and just let me know if any issues come up. Okay, so I'll also open the manual for reference here. Yeah, so this is the user manual, and we will start from the section 2 here was indicating the system requirement. So I'm hoping that most of us have access to Ubuntu based machine. So then I'll go to section 3, getting started of this manual. Please go to this section and we'll start running the tool from here. So for downloading the source code of Comet that we'll use, the version that we'll use in this session, please download the tool from this link that is specified in the manual. And then, like if you haven't done it before, please run section 3.2, which highlights what dependencies are required to run our tool, and also set up and compile the tool. So I have a compiled version of tool at my end. So I will begin from step 3.4, but please feel free to run step 3.1 to 3.3 in background, and you can see my screen to just see how the tool works. So first we'll go inside a Docker. Now we are inside a Docker, which I have already compiled the setup. So for me, it wouldn't take much time, but in your end, anyways, this compilation would hardly take few minutes. So please run that make command at your end. Yeah, so now we are, I hope the font size of my terminal is okay. Otherwise, I can just increase the font. So once we are inside the Docker, we'll go back to the code path of our tool. Yeah. So now here we are inside the Docker, which means I've completed section 3.4 of the manual. And for people who are who are using proxy, who are working from behind the proxy, there are steps to just make a couple of changes in the Docker file to get the system up and running. So please follow the steps that are specified in the manual. Now, once we are inside the Docker, we'll first run the make command. So this make will compile our tool. Next, we'll compile the thermal simulator, which is hotspot. So following instructions from 3.5 and running make. Now running instructions for 3.6, which is going inside the Docker, running the make run command and returning back to the returning back to the path of Comet main, which you might have downloaded. Instructions from section 3.4 to 3.6, they will hardly take 3 to 4 minutes. So please make sure you are with me. So now I will go ahead and run a simulation, for which I need to go to the path of the micro benchmark that I've specially created for this session. So it is inside the test lab session folder, and we'll first run make clean just so that getting rid of previous run files, and then we'll run the make run command, which will run the simulator. If you are please focus on the screen. I'll try to indicate certain things that happen during the simulation, which are an indicator that the simulation is running fine. So running the application would take around 10 to 11 minutes, depending on the size of RAM that is there on your laptop or machine, whatever you're using. So for this session, basically, we are going to run, while the simulation runs in background, I would like to go ahead with the slides that we were discussing. So for today's session, we'll be running like 3 simulations basically. In one simulation that I have currently run, there is no explicit thermal management that is going to get triggered even when the temperature tends to reach the thermal limit. The second simulation, we would be implementing a simple DTM policy in which the entire 3D DRAM will be sent to the standby state, and we will see the performance penalties that get introduced in the system because of thermal management. However, there could be, instead of sending the entire 3D DRAM to standby state, there could be more intelligent or efficient DTM policy with the goal to reduce the performance penalty. So the third simulation, we will implement an efficient DTM policy where only the heated DRAM dies are sent to standby state, and we will see that how does the execution time of that micro benchmark that we have run, that reduces when we go from a simple to an efficient DTM policy. So that is the overall agenda for today's session. So yeah, let's see. So the simulation has begun, and I'll open the intermediate log files that get created and try to show you the meaningful thing that indicates that the simulation is running fine. Okay. So here is the log file. You can also open log file using any editor of your choice just to see what logs are getting generated. So if you search for dram.bank in your editor, so you can see here that as I indicated earlier, that in the performance simulator part, we have augmented a memory access trace collection tool, which actually gives us the DRAM access counters, both the read and the write counter at an interval granularity. The interval that we have set in our tool is 1 millisecond, but you can tweak it depending on at what interval you want to run the thermal simulation. So you can see here that at every interval, we are able to see the DRAM access counts. So basically this string here, it represents number of banks. And in our 3D configuration that I'm currently simulating, we have 128 banks. And each of these count, it represents the DRAM accesses that are initiated for that bank, and we have segregated it as read and write for certain reasons. So now you can see that at the second millisecond boundary, the read counters also, the read requests were also made, write requests were also made. So the total access rate would be sum of read and write request for each bank. So yeah, just update this file for more log. Yeah, so basically you can see that at every interval, DRAM accesses are getting collected. And at the same time, these accesses are being fed to the power model, which is converting the accesses into a power number, which will be fed to the hotspot tool, and we will get back the temperature number. So now I'll open the power file for this simulation. So the name of the file is fullpowermem.trace. So if you open this file, you will see the header of this file indicates the component of that 3D memory. LC here indicates basically what happens is that it is a stacked architecture. So LC is the bottommost layer of that 3D DRAM, and there are some cores or some banks kind of structure in the logic layers. So we have named them as LC0 to LC16. And as we go forward, we have all the like B0, B1, B2. These are for the banks and all the way until be 27, which means there are total 128 bands. And at every interval of 1 millisecond, we are reporting the power consumption. This is the dynamic power consumption. So if you see here, depending on number of memory accesses that were initiated for the bank at that interval, the dynamic power dissipation is calculated for different bands. And these numbers are fed to the hotspot tool, which will report the temperature. So now I will open the temperature file. So the name of the file is full temperature mem.trace. You can also open and check this file. So here we see that again for those 128 bands, you can see corresponding to whatever temperature, whatever power number was fed to the hotspot. Hotspot has some internal thermal modeling that it uses, and it outputs the temperature number for the corresponding bands. So as you can see, as the time progresses, the temperature of bank 0, it's rising from 70 degrees all the way. It has already increased up to 78 degrees for certain bands. So basically, this 70 degree is the initial temperature that we start our simulation with. And these numbers, they are derived based on some steady state simulations that we perform, and the ambient temperature that we use. So that's why the simulation begins from 70 degrees, and depending on the memory access count of every bank, the temperature, the new temperatures are computed. So this is the tool flow, starting with memory access count, then going to the power numbers, and then finally the temperature numbers. So these are the 3 files of interest, I would say, in our whenever we are trying to develop some thermal management policy. These are the files which we will closely monitor and just try to gain insights either about the application behavior or about the system condition and come up with an intelligent DTM. Yeah, so let's see how far our simulation has proceeded. I think it will still take some couple of minutes to finish. So while this simulation is running, actually I have pre-saved some the video that the Comet tool generates for the 3 simulations that we are going to see today. So meanwhile, I'll just try to play that video just in the interest of time so that we can discuss further when the simulation finishes. So what happens is that this tool will generate a series of images, 1 image for every interval, and then all these images are stitched together, and they result in a video which will show us how the temperature changed over time. So I'll just try to play this video on my machine. Yeah, so this is the architecture that I have simulated, where we have a 3D DRAM with layer L0 to L7, and we have a 16-core processing system, and it is organized in an off-chip manner. The memory is off-chip to the core. So here you can see the time step that the tool reports that at 1 millisecond, this was the thermal map of the core and the memory. Here, this scale represents the temperature gradient. So the blue color represents low temperatures like 65, 66, and the dark red color indicates higher temperatures like 80, 82. And here we have shown a 2D view of the bottommost layer, because bottommost layer is farthest from the heat sink. So it will exhibit the highest temperatures. So we have shown the 2D view, the top view of bottommost layer. All these things are customizable in our tool. If you want to see the top view of any other layer, you can just tweak the script, and that should be good to go. So if I play this video, please try to note the change in the color of these structures, both CPU and memory. So as the simulation proceeds, by 3 milliseconds, the color has become yellow for cores, and the bottommost layer, top layers are still blue because they are close to the heat sink. So further, as the simulation proceeds, the memory is going towards even higher temperature. And towards the end, the bottommost layer has become dark red. So this is the I'll just play it again. So this is the situation when no thermal management is triggered, and we let the memory and the core reach whatever temperature they can reach with just without any external control of temperatures. So yeah, here the simulation that I had run, it has completed now. And to generate this video, the instructions are in the instruction manual, where you can just run this script called genvideo.sh after the simulation proceeds, and you can generate the video similar as I had just shown you. So this is the video that will show us the temperatures in absence of any thermal management. So next, what we are going to do is we are going to enable a default thermal management strategy, where I will just turn off the entire memory as soon as any bank of that 3D DRAM is close to the thermal limit. So for that purpose, what we are going to do is we'll have to edit the configuration files for this purpose, because as of now DTM is disabled, and to enable the DTM we'll have to edit the configuration file. So please follow the commands that are mentioned in section 4, where we go back to the home, the main path of the tool, and open using any editor, open a file called base.cfg, which is inside the config folder, and go to line number 332. So here, under the scheduler category, the type is currently set to pinned, and this pinned scheduler means we are not doing any thermal management. So please comment this line using a hash and uncomment the line 332, which specifies type of scheduler as pinned DTM, which means that we are going to enable the default DTM policy. Save this file and then go back to lab session or test lab session folder, run a make clean, and run another simulation. So we have run a simulation where we have enabled the default DTM policy that sets the whole memory into low power state, even when just a couple of ranks are close to the thermal limit. So this is very aggressive, like conservative DTM policy that we have enabled. So while the simulation is running in the background, in the interest of time, I'll also show the video corresponding to this simple DTM policy and highlight the performance penalties that occur due to a simple DTM. So just a second. So in the simple DTM, as you can see, the number of heat maps that are being generated are 26, whereas in the no DTM case, only 8 heat maps were generated. And as I indicated earlier, there is one heat map for every 1 millisecond, because that's the interval we have set. So this is an indicator that with a DTM policy enabled, the micro benchmark is going to take 26 milliseconds instead of just 8 milliseconds to finish the execution. And why has the execution time increased from 8 milliseconds to 26 milliseconds is because we are throttling the entire memory whenever there is heating in even some portion of the memory. So I'll play the video for this this case. So here, the time is progressing here. So we see that the memory has started getting red again, the bottommost die. However, notice the color change here at 10 millis, at 10, wait just a second. Yeah. At 10 millisecond, it was dark red, and I assume that now the DTM has triggered, and now it has throttled the entire memory. So the temperatures will start going down. The system will enter in the cooling phase, and you can see that the shades of red, they start getting lighter, and the memory has cooled down now. And again, when it is made active, again the color goes red, and again it will go in the cooling phase, and the darker shades start getting light. So there is this frequent heating and cooling cycle that the DTM engine invokes in the system. And due to this reason, the execution time, which was earlier 8 millisecond, it has now become 26 milliseconds. So there is considerable, like 3x performance penalty, roughly 3x performance penalty, just because of enabling a low power state space DTM mechanism. So I'll also show the log file that gets generated for this case of simple DTM. So as you can see here, so I'll just try to show the bank counters, and when the memory is throttled, we will see that the counts become zero altogether, because the memory is not accepting any more memory request for that period. So as of now, we see there are counters, there are numbers. However, okay, the simulation actually has not reached to the stage where we only have some 6-7 milliseconds of simulation as of now. So we'll have to wait a couple of minutes where we can see the working of the DTM engine. Are there any doubts so far? Okay, let's see if the memory got hot and we have already triggered the DTM. So, okay, not still. Maybe a couple of more epochs, and then the temperature will reach the critical limit of 80 degrees. So let's just wait. And again, like while we are waiting, I'll also describe the efficient DTM policy that we will run the simulation for in the next round. So yeah, in the efficient DTM policy, what we are going to do is that instead of suspending the entire memory, why not just suspend or throttle the portion of memory that is actually hot, and let the other portion of memory service the memory request. So what happens in that case is that all the cores would not get stalled. Only the cores that are mapped to the heated channels, only they will get stalled. And due to that reason, we are able to cut a little bit on the performance penalty. Okay, so here, as you can see here, that I think we have now reached the heated phase, and the cooling has begun. So I'll just take you to the counters. Yeah, so during this time, it was the memory was servicing the accesses. However, uh, there is this log that we print, which indicates printing bank states. So if we see this log, so actually this is the simulation that I have actually run was not for simple DTM, it was rather for efficient DTM. So the heated ranks, they have actually been turned off. So the bank state of 0 indicates that these particular banks and therefore those DRAM dies, they are in the low power state. Okay, I think we'll just let this simulation finish so that we can see the log in a single go, and that will give us some perspective of how the DTM works. So yeah, meanwhile, for the efficient DTM policy, what we are going to do is that in this file, which is common scheduler pinned DTM.cc, in the line number 81 is the function which is actually responsible for invoking the DTM. So there are two variants of DTM that are currently implemented in the code repo that you are using. One is set DRAM state and the other is set tier state. So the DRAM state one will set the entire DRAM to low power state, and tier state will only set the heated tiers. So for the next part, you will have to comment this line and uncomment the other line, which is set tier state. And again, compile the repo and again rerun the application as mentioned in the sections 3.7 and 3.8. So yeah, that will basically enable the more efficient DTM policy. So if we see the temperature logs here, the full temperature file for the DTM case, you can see here that the bank 0 temperature started from 70. It went all the way till 79 point something, 79.75, and we have added some safe margins in our tool. So as soon as, because our critical limit is 80 degrees, so now the memory was temporarily suspended, sent to low power state, and now the temperature has started reducing. So we come back all the way till 78, 77, and till 75, whatever is the recovery temperature that we set in the tool. All these parameters are configurable. So this is the situation that happens, that once the memory got heated up to 79 or 80 in certain cases, as I mentioned, sometimes the temperature spills a little bit because of the way the memory accesses are getting generated. And then now the cooling will happen, and once the cooling has happened, only then will the memory accesses resume. So the simulation has completed now, and I'll show you the log files. So actually, I ran the simulation directly for efficient DTM instead of simple DTM, and we will see what was the impact of this particular DTM on this. So we can see here that this particular column represents the time, and it represents time in microseconds. So this is equivalent to 1 millisecond. So you can see here that the memory was servicing memory request till it got heated up, and after 8 millisecond, the initial bands which are in the bottommost die, they got close to the thermal limit of 80 degrees. So only those banks are being suspended here. Other banks are still servicing the memory accesses in their full capacity. So like this is an efficient DTM. Again, the corresponding counts for the heated banks are 0. Rest banks are servicing whatever they could serve. Of course, there would be some control and data dependencies across channels because of the application's data being mapped to several channels, if that's the case. So the memory accesses for other channels can also be little less. However, they are not completely inactive. So that is what reduces the performance penalty. So we can see that once the heated channels got cooled down, only then they were again again made active, and then they serviced the pending request and the simulation finished. So in this case, it took 22 milliseconds. whereas in the case of simple DTM, it took 26 milliseconds. So there is some fraction of performance improvement by just using a very simple improvement over the default DTM policy. So if I show the video for the efficient DTM, yeah, so this is the efficient DTM. So you can see here that as compared to default DTM, these colors were mostly blue because uh, whenever heating was happening, even top dies were being set to standby state. So they were mostly always dark blue because their temperatures were not allowed to rise and they were temporarily suspended completely. However, in this case, whenever the shades of higher shades of red is reached and now lighter shades of red will come up, these temperatures still remain similar. Like they won't go back to dark blue colors because only the heated channels have been sent to standby mode. So yeah, this is the other DTM policy. So yeah, this part finishes our three simulations, variants of three simulations that we had planned for today's session. Any questions so far? If you are not able to run the simulation in parallel, it's okay. Like, please let me know whenever you run them. We can discuss them further offline. This is how a DTM policy is implemented in the comment tool. The details are there in the code repo, the README file of the code repo. You can read and follow the instructions from there. So moving on to the next part, because we only have 5-6 minutes to spare. I'll try to quickly discuss some other features of comment that might be useful to some of you in your respective research. So yeah. Okay, so as was indicated in the first part of this session, that Comet supports various Comet allows you to implement various thermal management policies such as task mapping and task migration and swapping, etc. And it also allows you to write your own DVFS mechanisms. So I'll quickly try to point you to the right APIs that you can use in order to just implement these DTM policies, write your own custom policies. For example, your policy could be whenever an application is running on a hot heated core, you can move it to the coldest core. That could be one DTM mechanism, or you can move the application. You can migrate the application to the core that is connected to the coldest 3D DRAM channel, or you can migrate the application to the core which is minimum utilized, which means that its temperature is not significantly high. Or your DTM policy could be that migrate the application to a core that is surrounded with the cold neighbors, basically, because there is thermal coupling between neighbors as well. So these are some simplistic DTM policies that you might want to implement. So I'll point you to the right APIs that you can begin your implementation using those APIs. So yeah, I'll just okay. So in order to write, we have provided like well-defined APIs in the Comet tool, which can be used, and the users can implement their own custom task mapping and migration policies. So for example, uh, if you want to implement a coldest core policy where you want to migrate your task to the coldest core, what you need to do is this user manual is already available in the GitHub repo of our tool. So you can actually we have already provided skeleton codes for implementing such policies, where you can just go to these files. Like you can go to the respective files like scheduleropen.cc and search for functions like this init mapping policy, and you can specify your own policy here, whatever it is, based on your DTM mechanisms. And then we have provided the skeleton code to also implement the policy, and how your policy will be like triggered at every interval. So all that code is in place, and you can just use these APIs to extend the tool Comet for your use. So if I go in detail, for example, if I want to implement a policy such as coldest core, what I would be doing is essentially this. So we have provided sample codes for a coldest core policy, where these are the classes that you will have to inherit. The base classes are already implemented. For example, mapping policy class, they are already they are in place, and you just have to inherit the right classes. And you will have to implement functions like this, a map function for your coldest core class, and a migrate function. So basically, when you implement these two functions based on your requirements, you should be good to go. So yeah, this is another thing that we wanted to highlight, that using the APIs is pretty simple in Comet, and we have already provided enough code like skeleton basically to just go ahead with the implementation. So for example, here what is happening in this custom mapping policy is that, so Sniper Simulator, which is integrated with Comet, it has its own mapping policy, which actually imitates a real kind of FCFS scheduler, first come first served kind of scheduler, where an incoming task will be mapped to the first empty core. So if you want to define a new kind of scheduling or mapping, you can just use these methods like which will give you the temperatures of the cores, like available cores and their respective temperatures, and you can figure out which would be the coldest core amongst all the available cores, and then you can deploy your incoming task in that very core. So yeah, these functions are in place. Feel free to just use them, and if you have any difficulties in adding code, or then you please feel free to send me an email, and I should be able to help you out. Yeah, so this was the part of hands-on. I hope that some of you who had access to Ubuntu machine, they were able to run simulation. Yeah, I'll just, yeah, are there any questions? We have 2 minutes to go, so I can take some questions.
Okay, thanks very much for your nice presentation and the hand-on exercises. I wonder
Sure.
how frequent you maintain the GitHub GitHub
Yeah,
issues. Yeah.
Okay, issues. Okay. So basically, we do try to respond to them on an urgent basis. However, the response time, usual response time is 1 to 2 days. So
Yeah.
I think if you have any issues, please feel free to post them on the GitHub repo.
Okay, thank you. Yeah.
Yeah.
Very nice. Yeah.
So I have a couple of questions.
Okay.
What's the exact application you were running with this simulation, and how do you fit the application to your simulation?
So basically, we run the I'll just open the application also. So for this, because I wanted to keep the simulation time less, because as we know that simulation times could be very high. So for the sake of this lab, we had a very simple micro benchmark, which was just like accessing and updating values into a large array. And why large array? So that most of the memory requests become cache misses, and they go back to all the way to the off-chip memory. So it was just accessing a large array and just trying to trying to populate some random values in that array. And what we do is that there are some, if you're familiar with Sniper Simulator, there are knobs using which you can specify the region of interest, so that the simulation will happen only for that part of code. So I have purposefully set my region of interest as the code that will definitely result into very high DRAM access rates, because I wanted to illustrate or demonstrate heating in the memory. So this is a very simple benchmark. However, I would like to mention here that the Comet tool, it supports several benchmark suites like spec benchmarks, parsec benchmarks, or splash benchmark suites. So the instructions are all there in the README file of the GitHub repo. And we also support the C++ implementation of deep neural networks. The instructions to run those networks are also in the README file of the GitHub repo. So how do I plug in this application is that Sniper basically supports two modes of running. One is the binary, just compile the source code and run it as a binary. Other is a trace-based execution where I record and replay the traces basically. So for my test program, I have created these pipes, which are from the Sniper simulator. So I record the execution, the memory accesses that would be initiated while that application is running. And then during the simulation, I simply replay these traces. So basically how to record the traces, the instructions are, the commands are already there in the run.sh file of this make file. So there are utilities like mknode, which you can use to create pipes, and then Sniper provides us the utility. This is from Sniper authors. We use this to just record the trace and replay it during the simulation. Does that answer your question?
Yes, thank you very much.
Okay. Sure.
I have a follow-up question. For your work, I read your work is which was published the ES last year. You mentioned that you partition the DNN that inference work to different layers. Then I guess you use the darknet. And how do you do the partition of different layers?
Okay.
And then
so basically,
make it embedded in the this commit software. Yeah, thank you.
Right. Yeah. So basically, in the Comet repo that I have shared with you guys here for today's session, it does not contain darknet. However, on the open source repo, we do have darknet code embedded here. I'll just try to, if we have like a couple of minutes, I'll take. So if you go to the test folder of online Comet repo, you will see here that we have darknet folder.
Yeah.
And inside this darknet folder, the source code of darknet, like for example, if I want to just mark a single DNN layer as, because we mentioned that we do offline profiling, right? So there are functions like if I want to profile just single layer of a neural network, so the relevant file where the forward pass happens in this darknet source code is network.c. So you can actually go to network.c. I'm forgetting the exact function. Yeah, it's some forward or something. So there is, this function. So for example, this function here, I'll just increase
Elja,
the
do you want to
font
share your
size.
screen?
Oh, sorry. I disabled screen sharing. Yeah, sorry about that. Okay, is the screen visible now?
Yeah.
Okay, so basically this network.c file, which we have in the darknet repo, this is the forward pass of that neural network. So here you can just annotate this code. You can just do some loop unrolling here and then mark those region of interest that Sniper allows using sim_ROI start and sim_ROI end. So then you can partition the neural network and you can profile the neural networks layer wise.
Okay.
So you will have to do some code annotations, some loop unrolling, some other kind of optimizations, just so that you run a simulation for each layer. And also you can also do some automation here. You don't have to do all of this manually, where you can just communicate, like you can use a file basically just to communicate which layer number is being currently run. And then you can dump the data corresponding to that layer on some log file. So all of that is possible. I have added the instruction of doing all this stuff in the README file of Comet. So if you go to Comet README file section, just a second, section 3.6, support for parsec, splash, spec, and deep neural networks. So if you run here, if you follow these commands, you can do pretty much like layer-wise partitioning. And if you have any issues, please feel free to write to me. I can help you out.
Okay. Thanks, Tom. Yeah.
Yeah, earlier my screen was not shared. So for the last question, that was how are we running the application, like binary or whatever. So basically, this is the makefile that I was talking about. So we generate the traces for the application. I'm running 16 instances of the application here. So using this run.sh script, I'm generating these traces, recording the traces and replaying them like during the simulation. So Sniper does provide these APIs like record trace, these scripts basically like record trace to just record the memory access execution of a program. And we can use record the traces and then replay them during the simulation. Okay, are there any more questions?
Since we are past the
Yeah.
time, maybe we can stop here. Yeah, Hosiok, are you still there?
Okay.
Yes.
Okay. Thank you, Hosiok. You can take over. Yeah.
Yeah, thank you, Preeti. Thank you, Salja, for the great work. I wasn't fully able to attend. I wasn't able to fully attend this session, but I saw that it was kind of, interactive session with hands-on. So thank you for the great work and thank you for the great session. So we are going to upload this video to YouTube. So I think you have already agreed to that, right?
Yeah,
Yes.
that should
Yeah.
be fine.
Yeah. If you need a file, then I can share it with you and we will anyways upload it to YouTube. Okay, thank you. Then that's it for the session and thank you for joining us and see you around.
Thank you, everybody.
Bye-bye.
Bye-bye. Thank
Thank
you.
you.
Thank you, everyone. Yeah, bye.
Bye.
Bye-bye. Have a nice